welcome to the last session of the school and also last session of today. It was a long day, and I'm happy that still we have you here. We are honored to have Jeongeun Park. She's a postdoctoral researcher at KUL, Catholic University Leuven. She is famous for her work on research and working on fully homomorphic encryption, and we are honored to have her in this session. So you can start.
Okay, thank you for the introduction. I'm Jeongeun. It's nice to see you guys here, even though it's a virtual conference. I'm really happy to give a talk in this conference. So I hope you guys enjoy this talk. So I'm going to talk about applications of FHE, especially to privacy-preserving protocols. So when it comes to FHE, outsourced computation is the most typical scenario. So there is a client who wants to retrieve data or compute data, and then client normally has no much computation power. So clients require someone to do something like computation over a bunch of data about her, and then she wants to retrieve the result. But the data can be confidential. So she wants to hide the private information, but she wants to get the desired function value. So we can use FHE to do this in a non-interactive way. So she can ask a server to do this by encrypting her message under FHE, then server computes everything and then gives back the result to the client. And the result is also encrypted under her key, so she can decrypt the function value with her own secret key. But FHE is not always the best solution for privacy-preserving protocols. There are some pros and cons. First, single server scenario is possible. Asymptotically, optimal communication and computation complexity is also possible with FHE. Moreover, non-interactive protocol is possible. So client can go offline freely at any point. However, communication cost is high compared to the other methods. It's because the size of ciphertext is huge compared to the underlying message that incurs communication cost high. And also computation cost is very high. The homomorphic operation is not cheap operation. So we are going to study a few examples of such protocol, especially focusing on how to serve these negative points in the next sections. So in outsourced computation, server does all the computing. But can we trust the server? Because the server is owned by companies. So if we trust him, we trust him. Sir?
I missed Karim, do you have the same problem? I missed.
No, it's fine, Hadi. We are continuing. It's okay.
Okay.
Sorry, is there any problem?
No. Sorry, go ahead. Hadi had a small problem. I mean, it's okay.
It's an office site.
Okay. So we have to assume that the computing part is semi-honest in if the protocol is using FHE. The semi-honest party is the party who follows the protocol honestly and correctly, but he wants to know the public elements and the messages transmitted through public channel, but it cannot deviate the protocol. It cannot change any inputs and outputs or abort the protocol, etc. So it should follow the protocol, but it can get some information from public messages. So the security of FHE in the CPA security is actually enough for this security to guarantee the client security against semi-honest party. So the client's input data, which can be confidential, can be securely preserved during the computation with FHE if the server is semi-honest. If you want to go for malicious adversary, then you have to include other primitives like zero knowledge and something else. Only FHE can guarantee this security against semi-honest party. And then the first section is the private information retriever. Now, private information retriever is the two-party protocol where a client wants to retrieve one item of database owned by a server, and the server should give the correct answer without learning which item she wants to retrieve. So, for example, if you want to search something through Google, but you want to hide what you're searching because it can be confidential data. So by using PIR, you can obtain the result correctly without revealing what you're typing to the Google. So there are two types of PIR. First of all, information theoretic PIR. The computation cost is very cheap because it only does XOR operation for each entry, and the security is very strong because it guarantees information theoretic privacy. However, if they only have single server, the optimal communication complexity is linear in the number of database, which is huge. So they have to assume there are multiple servers and the servers are not colluded at all. This is very strong assumption in practice. There is another one called computational PIR. The advantage of it is that you can only use single server under cryptographic hardness assumption, and you can have sublinear communication cost with a single server only. However, the computation cost is very high because it uses cryptographic operations. Since we are focusing on homomorphic encryption, so I'm going to talk about computational PIR only. So there is one first attempt to build PIR protocol based on FHE, which is called XPIR. Their naive approach is like this. The database is structured as a vector of dimension n. For example, n is just 25. And the client wants to retrieve the third item. Then the client prepares a data query, which is a vector as well, of dimension n. And only the third component is an encryption of 1, and the others are encryptions of 0. And it sends this query to the server, and the server computes dot product between two vectors and to output the desired item, which is encrypted. So it's very simple, but the query size is very huge. It's linear in the number of database elements. So if n is 1 million, the network cost will be very huge. So they have another method to reduce the complexity of query to sublinear in n. Their idea is that to structure database as a matrix, like square root n by square root n matrix. So for example, we have also 25 elements, and the client wants to retrieve this data located on 3.2 position. So to retrieve the third row, the client prepares a row query where the third position is an encryption of 1 and the others are encryptions of 0. And to retrieve the second column of the third row, client prepares the column query in the same way. So after server gets these two queries, server does vector matrix computation in this order, and finally he gets the encryption of desired item. So in this way, the number of ciphertext for query is reduced to 2 times square root 2 when d is 2. So it's actually sublinear. And later, another approach appeared called CLPIR. So they actually optimize the size of query. Instead of sending square root 10 queries, they compressed all the necessary information in one ciphertext. They encode the index of desired item in the exponent. So instead of giving square root n ciphertext, just sending one ciphertext is expanded to this desired vector by a server with homomorphic operation. So instead of d times d square root n, the client only sends d ciphertext. This is an optimization. However, the server has to do something additionally to expand this query to the desired format. And this procedure takes d times d square root n. And also, both protocols, they used BFE for their implementation and instantiation. And BFE has expensive multiplication in terms of noise growth. The noise grows quadratically in depth, multiplicative depth. So that's why they want to avoid this expensive operation. Instead, they use plain text ciphertext multiplication. So as we saw here, this query is encrypted and the database is public in server's view because it's owned by server. So here you can do ciphertext plain text multiplication easily without changing anything. However, the outcome after this multiplication is an encrypted vector. And you have to do one more dot product between encrypted vector and another query vector. So to avoid this kind of expensive operation, they splitted one ciphertext into F chunks. F is cryptosystem's expansion vector, which is a ratio between ciphertext and plain text. So each chunk is actually size of plain text. So you can do plain text ciphertext F times. Instead of one ciphertext operation, you do F times plain text ciphertext operation to avoid large noise growth. If there is large noise growth, there is a high chance to have decryption failure at the end. So yeah, nobody wants to have a decryption failure, but that's why they use this trick. But this has a problem when it comes to the reply sides. Because they do F times this operation, the size of answer is also grows proportionally to F. So there is F vector, actually in precise, F to the d minus 1 vector exists in the reply sides. And there is another approach called Shakespeare. They don't use matrix vector multiplication. They have different approach. The query is an index, and the index is binarized first. And then they extract these epsilon j's, which is bit, and they encrypt or is epsilon j's. So the size of query is log n. So that sends the log n ciphertext to the server as a query. And then the server stores their database elements as a lookup table, as you can see below on the right. So data is arrayed like this, and the index is binarized as client prepared. So zeroth data is here, and in the next column you have binary representation of 0, and you have binary representation 1, and etc. So this is the database that server structured. And server runs n-1 times homomorphic MUX gate, which is called CMUX in TFHE paper. So what does it do is one MUX gate outputs one ciphertext out of two. It takes two ciphertexts as an input, and it chooses one of them depending on the controller bit. So here, the controller bit is an information of index. So data is structured like this, and this one is from client. Client encrypts all the binary information of index. So if epsilon0 is 0, then all the database who has 0 on this position is selected in this round. So we run n over 2 CMUX gates to select desired item. And then among these n over 2 selected items, we run another round of CMUX gate with the next query. So after log n times of round of this, at the end, server can get just one element, which is the desired item of data. And then the server gives the result to the client. But log n ciphertext as a complexity, log n is way better than square root n. But still, in practice, we want to pack all the ciphertext as one ciphertext, as CLPIR did. So we can use actually the same technique. So first, the index I is binarized, so you have log n bit value, and instead of encrypting these log n values individually, we can embed all the epsilons to the coefficient of a polynomial. And then we can encrypt this one polynomial as a query. So instead of giving log n ciphertext as a query, server can get just one ciphertext. However, to proceed the aforementioned process, server has to unpack all these epsilon j's into log n ciphertext. And this step takes a log n operation. So still, compared to CLPIR, the complexity is log n compared to square root n, which is way better than previous work. So query unpacking, as I said, it takes a polynomial which has all the information in the coefficient, and homomorphically it unpacks log n ciphertexts, each of which encrypts corresponding coefficient. And this additional complexity is log n. So we can see the comparison of complexity of previous works. So XPIR, CLPIR, because of their choice of homomorphic operation, they have F factor here. But Shakespeare, instead, when they instantiated this CMUX gate, they used TFHE external product, which is cheaper in terms of noise growth. The noise grows linearly in the multiplicative gate, multiplicative depth. That's why they don't suffer from this F factor. So they can achieve constant answer size, and query size is log n compared to square root n is better. And then they also do the same technique as CLPIR did to pack the query in one ciphertext. So it's actually divided by the degree of polynomial. And then the main computation time, this L is FHE parameter. Since Shakespeare used TFHE, this L comes from TFHE parameter. So that's why, because of L, Shakespeare has more operation during main computation. However, if we compare only the complexity query and the query unpacking step, that Shakespeare has the most optimal complexity. And recently, there is another paper called Onion PIR. Actually, this Onion PIR people implemented their computation with the external product that Shakespeare used, so that they can remove F factor at the end. However, the other complexity remains same. So is there any question about PIR before going to the oblivious run?
Okay, thanks. Is there any question? Mahdi has a question. This is clear that FHE is not CCA2 secure. Is it possible to create a CCA1 secure FHE scheme?
Well, there is a theoretical result that shows the possibility, but it's not instantiated yet.
Okay. Mahdi, did you get your answer? And if you want to talk also, you can raise your hand, then I can enable your microphone. Okay, he said thanks. Another question? Okay, good, we can continue.
Okay, the second building block is, second privacy preserving building block is oblivious RAM. Oblivious RAM is a cryptographic primitive which allows a client to hide access pattern. When the client accesses the storage, which is a server, she wants to touch some data, or she wants to write something on the storage, but she doesn't want to reveal her access pattern and also which item is she wants to touch. So ORAM can solve this problem. The query consists of 3 elements. Alpha is an address of the item she wants to touch. Operation is either read or write. And data is something she wants to update. So if the operation is read, the data is just a random thing. And the answer should be the desired item. And if the operation is write, the answer is just something random, because if she wants to write something, she doesn't need to get the correct answer. So it looks similar to PIR, but it's quite different because ORAM offers write functionality, which means if the database is public and the client wants to write something here, then the server immediately notices what is changed. Then she reveals her access pattern and which item was touched. So it breaks the security of ORAM. So ORAM cannot be used for PIR directly, since the data should be encrypted under client's key. But PIR is possible for a public database. So this is the difference. So ORAM was first introduced by Goldrich and Ostrovsky in 1987. The ideal ORAM design should achieve low computation overhead for client and low bandwidth blowup, which is the ratio between communication cost of ORAM and the non-private case where the access pattern is not hidden. So initially, ORAM was designed in classical model, where the server acts as a plain storage device to support only read and write operation. So to hide her access pattern, clients has to do all the jobs, all the computation, and also client has to interact with server multiple times. Therefore, at least log and bandwidth blowup was inevitable in this model, where n is the number of data elements. And later, people started to think about server computation model, where the server does something else other than read and write. So, which is more realistic for the cloud storage scenario, because normally server stores something and can compute something as well. So, in 2016, one paper shows that it's possible to achieve constant bandwidth blowup if we use homomorphic encryption. So I'm going to talk about the existing ORAM based on FHE. So previous server-aided efficient ORAM structure looks like the figure, like the tree structure. So n data elements are distributed in this tree of depth log n. And the client needs to maintain the state of the database locally. Server only touches one path, which is indicated by client's query. For example, client says, okay, touch the nodes on this third path. And the server does the following thing. So that's why logarithmic complexity in terms of both computation and communication was possible. And each node, called also bucket, consists of Z number of blocks, and each block is either an encrypted real data element or encryption of 0 under an FHE scheme. And client knows where real elements are stored in the tree via setup phase. And client asks a path and a block per node on the path to be touched. Then server homomorphically adds up all the requested log n blocks. So I will show you the example in the figure. So this is the database owned by a server. The n database elements are distributed in these n buckets. And client knows already where the desired item exists by setup phase. So she specified the path first, which is 3. So from the left, this is the third path. And then she indicates touch the second block of the first node and touch the second block of the second node on the path and touch the third block of the third node. So the server follows the same way, the protocol. So he chooses the indicated blocks and then adds up everything. Since the real block exists in one of the 3 blocks and the others are encryption of 0, the addition doesn't harm the correctness. The addition outputs an encryption of the real data block. So this is how tree-based ORAM based on FHE works. So far, the server does reading the desired item, and then he gives back to the requested one. However, when does writing happen? Server proceeds the same protocol as I described before, and the server stores all the queries at the root until the root is fully filled. So since the root also has Z blocks, so it can actually store up to Z number of queries. And then once the root is full, server runs an interactive protocol called eviction with the client to empty the root and move blocks towards the leaves via reshuffling all the blocks of buckets on the specified path. So eviction is a necessary protocol to achieve correctness and security, because server contains n elements, but in one access, he doesn't touch every element. He only touches log n specified elements. What if the client touches the same block again? Then it reveals something. Then the server can notice some similar behavior compared to the previous behavior of the client. So the same blocks which were touched before shouldn't be touched again. Then, since the server doesn't touch everything, some information can be leaked. So to avoid this, client and server have to reshuffle all the data to distribute somewhere else in certain times of access. This is called eviction. This is done during eviction. So, in other words, in every Z number of accesses, eviction should be run to guarantee security and correctness. And during eviction, the requested update values are stored in the desired position. Because eviction does reshuffling, so this item field in the root goes to the desired place according to their address. So during eviction, the requested data from the query stored in the root, it goes to the position where it's supposed to be. So writing also happens during eviction. And eviction protocol is considered as offline phase because it doesn't depend on query. However, actually the client should be online to run this eviction protocol. So there are some pros and cons about this previous approach. The communication complexity is log n because it only touches log n blocks. So the client sends log n addresses. And therefore, bandwidth blow-up can be constant. And this online computation complexity, which is server's reply, has log n complexity as well because it only adds up log n blocks. And in practice, the running time is really fast because it only consists of homomorphic addition, which is very cheap. However, the server's memory overhead is large because the n elements are distributed in n nodes, and each node has that number of blocks. So in total, they have to store z times n ciphertext in server storage. And eviction is an interactive protocol which requires multiple interactions between server and the client. And the client should be stateful to keep the database which will be redistributed via eviction. So she has to keep up where the existing data is stored right now and where will be gone after one eviction. And eviction consists of heavy homomorphic operations to reshuffle blocks of log n buckets. So therefore, actually this homomorphic operation has hidden large constant factors, which is z log z. And in practice, this factor is 2 to the 13, which is quite big. So this can actually be a downside of the instantiation of this protocol. And client has to keep some parts of data to help eviction, which requires somewhat large memory consumption for client side. So this is not very suitable for fully outsourced storage scenario. So what can be the requirements for the fully outsourced storage? Non-interactive protocol should be achieved, and stateful client who can go offline freely at any point. And it's better to have little client effort in terms of memory and computation, because normally client has limited power of computation source. That's why it's better to have less effort as much as possible. And for practicality, low bandwidth blow-up and low latency of server is also desirable. So there is a recent work, which is non-interactive and stateless ORAM based on FHE. It's called Panacea. This is actually my recent work, so I'm going to introduce this for the first time in this conference. So the query consists of 3 elements, as it's the same as previous ORAM. So alpha is an address of the item which she wants to touch, an operation, and the update value. And since in this scenario, client doesn't give any information apart from query for the computation of server, which means client is stateless. And that's why the server has to touch every element to give the correct answer and to guarantee the security. If the server doesn't touch every element, which means server knows something, which element he can touch or which element he can rule out, which breaks the security of stateless design. That's why computation complexity is ON. It's inevitable. And communication complexity is log n because it asks only a bit representation of the index. So there are some building blocks of Panacea. So we need a small circuit, which is called CMOS gate. It takes 3 ciphertexts, and the first one is called controller bit. And depending on this bit, it outputs one of the 2 inputs. So if C is an encryption of 0, it outputs encryption of A. Otherwise, it outputs encryption of B. And there is another algorithm called homomorphic demultiplexer. So it takes an encrypted bit representation of a positive integer A, and it outputs an unit vector where the 8th component is an encryption of 1, and the others are encryptions of 0. So we start with an empty tree except the root. So root has the value 1 and the others have 0, this is the initialization of the tree. And after each computation on each level, the root value is homomorphically copied to the desired node. So if the controller bit here in this level is encryption of 1, it goes to right. If the controller bit is encryption of 0, it goes to left. So by doing some homomorphic computation, we want to copy this root value to the desired leaf. So how do we do? First, we choose the desired leaf index, which is 3 here. So from 0 to 7, the third element is here. So we want to copy this 1 to the desired position here. And we binarize this 3, which is 0, 1, 1. And we take from the most significant bit to the towards lower significance bits. We start from root value 1, and we take the first most significant bit, which is an encryption of 0. So what we want to do is to move 1 to the left child node if the controller bit is encryption of 0, otherwise it goes to the right. How do we do? By doing this computation on every child node. So in on the right child node, on every right child node here, it does the computation this with the value of its parent node value B and its corresponding controller bit. So let's denote the parent node value B here, and the controller bit is denoted by large C. And each node of child node is denoted by small c. So let's start from the root. Since the controller bit in this level is an encryption of 0, it should go to the left side. So let's check if it's true. So left child node C here, it takes C1 here, and 1 minus C1 is encryption of 1 minus C1 is encryption of 1. And B is 1. So 1 times 1 is 1. So it remains, it's changed to encryption of 1. And we check the right child node here. It takes a controller bit here, C1, and C1 is 0, so B doesn't matter. So it goes to, this value goes to 0. Since the parent node here is 0, the computation really doesn't matter because B is always 0. So all the lower child node values, which have parent node value 0, goes to 0 always. So we follow this protocol in the corresponding child node, and at the end we have encryption of 1 at the desired position, and we take the leaf value only. So client, as we defined before, client prepares a query, which is an index of encryption of index and operation and the update value. And server runs homomorphic demultiplexer to get a unit vector of dimension n, which consists of encryption of 1 on the desired component. And this homomorphic demultiplexer is run with this alpha. Alpha can be used for control a bit of each level. Since the tree has log n level, each component of this alpha goes to each corresponding level. So by using homomorphic demultiplexer, server client homomorphically indicates where the server has to touch. And server computes dot product between this unit vector and the database vector, then sends the result to the client. So since the desired item has an encryption of 1, after this dot product, it outputs the desired item, which is encrypted. And so this response does only reading. And we have to do writing as well. To hide the access pattern. To hide the access pattern, server has to do reading, writing together. So writing happens, how? So the operation is encoded as a bit. If the operation is reading, the encoding is an encryption of 0. And if the operation is write, this encoding is an encryption of 1. So we already studied how CMOS gate works. So if the operation is reading, it outputs the original data, and it's stored as temporary value. If operation was writing, it outputs the updated value, which should be written on the desired position. And with this temporary value, a server runs the CMOS gate again with the unit vector, which was computed after homomorphic demultiplexer. So homomorphic demultiplexer indicates where the server has to touch. So only the desired position is an encryption of 1, and the rest are these encryptions of 0. So depending on LJ, it outputs either the original data or the requested value. So if the operation was right, it outputs the updated value here, and only the desired position is changed to this update value via CMOS gate. So we note that the latency of the server only includes the response phase, because update phase happens after giving the answer to the client. So the latency only includes this response phase. So this looks very naive, and clearly it has to suffer ON complexity, which is not desirable for real-world applications. So since our construction doesn't rely on any specific data structure, there are more ways to optimize our design than tree-based approach. Because tree-based approach by default is difficult to be parallelized. But however, we don't have such specific design. So we can use parallel computation easily, and also we can make use of batch code method to amortize the computation cost. So what is batch code method? We are going to use probabilistic batch code as our optimization method, which is parameterized by the 5 tuple, takes n elements and outputs as m possibly distinct elements distributed among B buckets. So a client wants to fetch K elements from the original database by touching B buckets at most, by touching at most one element from each of B buckets with probability P. So let's see the example here. I took this example from CLPIR paper. So in a naive way, we want to touch the two elements at the same time. We want to ask two elements. In a naive way, the server has to run the protocol with this 4 elements which outputs single answer twice. It means to retrieve 2 elements, the server has to run this protocol twice, which means the server has to touch 8 elements in total. But we want more efficient way. So we have to set n, which is the total elements the server has to touch, should be smaller than k times n. K is the number of elements the client wants to touch. So here, instead of 8, we have 6 elements, and we have 3 buckets. So these 4 elements is actually distributed in 6 slots in 3 buckets. And client can retrieve any 2 set of elements by touching each bucket at most once. For example, the client wants to touch x1 and x2. Then for this bucket, client just ask this slot, and this bucket, client ask x4. And for this bucket, client ask this slot. So in the end, client received x1, x4, and x2, XOR x4. What was his request at first? It was to retrieve x1 and x2. However, clients get x4 and this value. Since this is x2 and x4 is XORed, you can actually receive x2 easily by running XOR between x2 and this value. So you can retrieve any 2 items by using this method. So we want to more generalize this method to large database elements. So to distribute n elements in B buckets in the server side, server has to use some hash functions. Here we say omega hash functions. And server structures a database as a simple hash table like below. So this is all hash values of all database elements with omega number of hash functions. And then the server group its items by hashed value, resulting in B times large B matrix, like this table. So these items in the first bucket, those items whose hash values are 1. And this item, their hash value is all 2. So it's actually grouped by their hash value. So this is the B buckets, and client has to touch each bucket at most once to retrieve K elements. So we have to parameterize B and large B to achieve which is smaller than K times n, so that we can actually get some computational improvement instead of running protocol K times. This is the most well-known technique. This is not our technique. We are using the existing technique, and I'm explaining the existing technique. So, in client's case, client has to prepare the query which touches B buckets to fetch K elements. And each of buckets should be touched at most once. This problem can be looked at as a boards and bins problem. The client has to place K boards into B bins, B buckets, where each bin can have at most one board. So to do this, the most well-known ways is using cuckoo hashing to solve the problem. So cuckoo hashing is a well-known technique, but I'm going to explain it briefly. So there are omega number of hash functions here, and there is a table of B slots. B is omega times K. And to insert an item into the table, we first sample a random hash function, and then we insert this X, the item X, and the index of hash at the location of hash value, HI of X. If the slot is empty, we can actually insert it without any problem. However, if the slot is already occupied by something else, which is Y, element Y, and the Jth with the Jth hash function, we kick out the old value and we insert the new value. And then choose another hash function which is different to the previous one, and then we recursively reinsert this old value into the table by using the same way. So by doing so, we can insert all the K items into B slots without any collision. So now, what we've done is very similar, actually it's the same as what SIL-PIR did to achieve multi-query with so much improvement. But we are doing ORAM, not PIR. So the difference is that client also do writing. Client can overwrite the existing file in ORAM. So in other words, since the batching technique requires redundancy of omega copies of data elements, and all these copies need to be updated with the same requested value for each write access. Otherwise, we might face data inconsistency. To avoid this, there is another solution which we introduce called consistency correction. So as I said before we update the value, we have this omega copies of elements are stored in the database. And after update, this element in the first bucket is changed to Y. But still, there's X2 somewhere exists in other buckets, here and here. But since each bucket asks a unique item, if this was already touched, the same item is not touched in the other buckets. Otherwise, it doesn't make sense because you want to retrieve K different items. You want to touch K different items, not the same one at the same time. That's why in the first bucket, something else was touched. That's why this same value remains the same. It's not changed yet. So the other two same X2 should be updated. Otherwise, we might have data inconsistency at the end. And for the simple explanation, I'm just writing everything in clear text, but in server's view, those look random. But since he's allocating all the data like this with omega hash functions, so he knows where the items are same and copied in the same way, but he doesn't know which item is encrypted and which item was accessed. Otherwise, it breaks the security of ORAM. So server knows where the redundancy per item occurs in the data table by using his hash table, but still doesn't know which item was encrypted. And so for simplicity, we set omega is 3. Actually, in practice, we use omega is 3. And server knows the 3 tuples of indices, the position where the same item is located. In our case, it was X2. So 1.1, 4.3, and B.2. So server only knows that the position here, the items are same. And let's make these values on these three positions same with the value, with the update value requested by the client. So what are the requirements? We need operation bits per bucket. So we are actually looking for this first bucket, fourth bucket, fifth bucket. So each bucket is assigned to each operation. So B1, B4, BB. But we already know that the first bucket is already updated, which means the first operation for first bucket was writing. So we know P1 is an encryption of 1. And those are, we don't know yet, but it doesn't matter in this case. And then we also need the unit vector, which is computed via homomorphic demultiplexer per bucket as well. So we are going to compute a new value for these three positions by computing this formula. So with our example, B1 is writing. So this one is 1, and we don't know before BB yet. And we already know that L11 is 1 because in the first bucket, the first position is changed. Which means after the homomorphic demultiplexer, the first component of the output is only the encryption of 1 and the rest are encryption of 0. So we know that L11 is encryption of 1. So this term is alive. However, since all the buckets since the client prepares all the different K unique indices, so no more or equal to 2 of LIJs or encryptions of 1. Since the bucket, the first bucket for X2 is already touched here, the other values should be 0. So L43, LB2, this term is just gone. So what is left now? Here, this term and this term is survived. We know this is 1 and 1, so it's 1 minus 1 goes to 0. So this term is also gone. So we have now this one survived. V11 is just a changed value y, and L11 is 1, B1 is also 1. So actually, V new is the changed value. So after this computing this changed value, the server puts this V new to these three positions. And server does the same thing for the next 3 copies of the other elements. He does until the full n elements are refreshed. So in this protocol also, this consistency correction also suffers from ON complexity, which is inevitable. Yes, so this is our overall complexity. So Panacea and stateful ORAM has a different design, but there are some pros and cons. So memory server, in memory case, we don't have Z factor because we don't have such tree structure, and we don't need to contain more data to guarantee the security. So that's why Panacea has less memory overhead, and omega is set 3, and Z is in practice 229. So stateful design, it has more overhead in terms of memory of server. And client as well. Client doesn't do anything apart from querying, so she doesn't need to store something else. That's why it has a smaller memory overhead. And Panacea is stateful, so it's not stateful, and stateful design is stateful. And computation of server is ON, but with the previous PBC, we can actually have amortized cost by just touching B buckets to retrieve K elements. So we will show you. I will show you the computation result later. So even though we have ON complexity, in reality, the amortized cost is actually practical. And the computation for eviction is not applicable in this scenario, whereas stateful design has some large factors here. So in practice, the duration of our panacea with PBC is actually practical when it comes to amortized cost. So K is 256. So client wants to retrieve K elements at the same time. And in total, it takes 300 seconds, but in amortized way, it's just similar to 1 second. So it's quite practical. And also we can make use of multi-threading assumptions. So we are actually using 36 threads for our computation result. So this is ORAN. Is there any question? I don't know how much time I have.
Yeah. So we have a couple of questions. Sharon asked, is not ORAN supposed to hide the access pattern too? And if yes, then does the FHE solution hide the access pattern?
Yes, it hides access pattern. That's why this ORAN protocol does reading and writing together. If he only does reading only, then the server knows, oh, the query is reading. So that's why it has to do reading and writing together.
Okay. Sharon, is it fine? Did you get your answer? Okay, let's go to the next question. Does the security change if one uses vector of zeros instead of E0? And he said vector of zero is also an encryption of zero. I think it's related to the page that I don't know, maybe 20 pages earlier. Somewhere you were talking about encryption of zero, and he's suggesting to use vector of zeros. Maybe here, or I'm not sure if I know the answer myself. Siva, can you please raise your hand and ask your question yourself? Let me know if Siva is here. Siva, I activated. I requested. I sent a request to you to ask question. Yeah, now your microphone is enabled.
It is regarding onion ORAM.
Yes.
The question is regarding the onion ORAM.
Yeah.
Where like you are like, there are some dummy data, right? That is encryption of zeros.
Yeah.
We could have directly used the vector of zeros, right? Like which is also an encryption of zeros.
Vectors of zero, but why?
Because like additionally we don't have to add the extra noise to the data. Still it gives the same output.
Yeah. I don't understand why we need a vector here.
Encryption is a vector. Encryption of zero is a vector, right?
Well, it depends on how you define the ciphertext.
Okay, yeah.
Okay.
Okay.
And any.
Also, like we could have added plain zeros instead of encryption of zeros without the noise. That's what I mean. Where the error term is also zero.
Sorry.
The encryption is the message is zero and the error term is also zero.
Address.
I think array.
Arrays.
No, I guess, sorry, it seems the question is that why we need this encryption of zero? Can we use just vector of zero? Maybe encryption of zero has randomizer. I don't know why you say that vector of zero. Vector of zero is deterministic thing.
Yeah, I don't, sorry, I don't get.
Yeah,
Okay, fine.
yeah. I mean, encryption of 0, it doesn't mean that it's 0. It's just something it's indistinguishable from encryption of anything else.
Yeah.
So you cannot use completely vector of 0. I don't know. I mean, maybe it's because of some reason, but this is a basically naive question. Can you use just 0 instead of encryption of 0? If yes, oh, it's okay.
No,
If
it's
not,
not.
why? Yes, then you cannot use it.
Okay, fine.
Okay, thanks, Karim, for your help. So Sufiana also had a question. I think you explained, but let me to ask a question. How the home-victim multiplexer works? I think you explained, but still, if Sufiana, you have question, I sent a request to activate your microphone. Do you want to ask your questions?
Yes, yes. You answer my question during the talk.
Okay. Okay. Thanks. Yeah, because this question belongs to I don't know, long time ago. So it was maybe I didn't want to interrupt you, and now we have this problem. But okay, anybody? Do you have any question? Okay, good. I think we can continue.
Okay, thank you. So we can go to private set intersection. So private set intersection is a two-party protocol where both parties holding their own data sets and they wish to learn the intersection of both sets while keeping the rest secret. They only want to compute this intersection, not revealing the rest. So as an application of PSI, we can think of private contact discovery as the most popular application. So I assume everyone here is using this messenger application like WhatsApp and Signal, and you want to know which friends of your address are using the same application. Without revealing your address book to the server. So to do this, we can use PSI because the server has a lot of database of the user in the world, and you only have a very small database size, and it's easy to compute intersection by sending your information to the server. So it can be an example, and also Microsoft and also Apple, Amazon recently, they offer a service called Password Monitor for clients based on PSI via homomorphic encryption to check if the passwords stored in this Microsoft browser, which is called Edge, have been found somewhere in the internet, through the internet. So actually you can use this service if you're using Microsoft Edge. And I believe Apple also offers the similar service. So this is the example of PSI. So from now on, we're going to talk focus on PSI for unbalanced sets, which means one set is way smaller than the other sets. So the common example is private contact discovery, which I said already. So there are extremely fast protocols based on oblivious transfer, which requires high communication complexity and multiple interactions between two parties. So actually, we can use these fast protocols for any kinds of scenarios. However, their downside is communication, which is linear in both set sides. So this is not desirable for unbalanced sets, because anyway, the communication is linear in the larger set as well. So we need something else for this unbalanced set scenario. So for this scenario, there was a work already based on FHE. Since they are using FHE, there is a non-interactive protocol, and asymptotically almost optimal complexity is achieved. And it gives better performance when one set is much smaller than the other set. And the computational overhead is still a bottleneck, but comparable to non-FHE-based protocols due to many optimization techniques, which I'm gonna talk about. So we can think about a naive approach. So server has large set, which is Y, and the cardinality of Y is NY. And server set's way smaller than server set. So NX is the cardinality of the set X, which is way smaller than NY. So client sends all the encryption of its value to the server. And the server computes the following for each xi. So it's actually comparing to see where if there is the same elements in Y, in sets Y. So encryption of xi is fixed, and it just computes the difference to check equality, difference with the or elements of set Y. So it has to compute if there is the same element here, it goes to 0. Well, encryption of 0. If not, it outputs just random element because of this random element. So it looks very expensive because it has to run NY times of homomorphic multiplication. Communication complexity is very okay. It's just linear in the small set size. It looks optimal. However, the computation is very, very large, and X times NY is too much to be practical. So they introduce an optimization method to reduce the computation time. So there is a ring isomorphism between this vector and this polynomial ring for the certain parameter sets. For a prime t, which is congruent to 1 modulo 2n, and n is power of 2. In this setting, there is isomorphism. So actually, you can use this property for SIMD operation. So here, you have ring element polynomial. So if you do ring operation over this ring, the same operation applies to the individual slots here. So by just doing one operation, you get n computed value at the same time. So we are going to use this technique to reduce the complexity. So if a client splits its set elements into nx over n chunks, n is the degree of polynomial, and each chunk which contains n elements is encoded via the map iota to the polynomial and encrypts this polynomial. Then the number of ciphertexts reduced down to O of n or x over n from nx. So it's much improved already. And also computation complexity is improved by a factor of n. And if n is close to nx, the complexity becomes linear in ny. However, this is not enough. With only batching technique of client side, server has to encode each yj into individual polynomial, resulting in preparing ny polynomials anyway. So this patching technique doesn't really help server's encryption time. Anyway, it's linear in the large set size. So which means homomorphic operation actually works between this ciphertext given by client and this encoding value of server. So here, clients takes all the advantage of using n different slots, but here server doesn't use the same technique at all. So in order to maximize the effect of this batching technique, server also needs to structure this data in a manageable format, letting him make use of the same technique, the same advantage as well. So we've learned the same technique before in ORAM section, but yeah, here PSI does the same thing. So server prepares k-hash functions and then generate a simple hash table like the figure below here. So server hash all the data elements and then stores every hashed value in one table. And then it groups its item by hashed value, resulting in M by large B matrix like this. So all these values have the same hashed value, which is 1, and this bucket as well. So we already studied the same technique before. For client side, the client also prepares the same k-hash functions as the server used and use cuckoo hashing technique to distribute all these NX items in different buckets without collision. So cuckoo hashing actually used in many different cryptographic primitives for allocating database. So this M buckets should be larger than NX to handle NX items without any collision. And we choose M is larger than NX. So each item is assigned to its unique bucket by using cuckoo hashing technique. So we use this hashing and batching together. Client parses the hash table into M over N vectors of dimension N, and then encodes its vector individually. So instead of just M ciphertext, client has M over N ciphertext, as we saw. So the client takes N value out of M here, and then does the same thing until it has all the items in ciphertext. So the client has NX over N ciphertext for the query. And then server parses each of B columns into M over N vectors of dimension N as well. So now he can make use of this batching technique as his optimization as well. So anyway, we are going to compare bucket wisely. So X5, if there is the same element which is the same as X5 here, then yeah, then we can continue comparing bucket wisely. And the server encodes its value with this by fetching N vectors in one encoding vector. So he actually parses each B columns into M over N vectors of dimension N and encodes its vector individually. So it actually results in B times M over N polynomials and perform PSI. So what is the improvement? The communication complexity was NX over N with batching only, but now it's a bit increased with hashing together because our choice of M was larger than NX, so it's a bit increased, but it's not that much improvement in practice. However, the computation is much improved since it also uses the same, batching technique. We use this N elements is encoded in one ciphertext. These N elements are also encoded in one ciphertext. So actually, we are touching M times large B over N ciphertext to compute whole NY elements. So it's actually reduced from NX times NY over N to K times NY over N. K is the number of hash function. And in practice, K is set to 3. And in 3 is enough to guarantee this, the correctness It's already proved. So it's much actually improved, and X, because K is 3, it's very much smaller than NX, so the computation is so much improved by batching and hashing technique as well. And another optimization method for complexity is called windowing. It's because in a naive approach, we have to compute this homomorphic multiplication ny times, which means the multiplication depth is log ny, and we have to do multiplication with r as well, so log ny plus 1, which is large to handle the noise. And at some point, since ny is very large, at some point we might have decryption failure. Then we have to run bootstrapping, which is very, very slow. So we want to reduce the multiplicative depth to handle the noise issue more easily. So we can rewrite this product as a polynomial, and the clients, if the client only sends C only, then the server has to compute C to the ny. But if client sends all power of C, so this power of C is given by client. And what the server do is a dot product between this given vector consisting of powers of C and other known value. So it becomes the multiplicative depth becomes 1. However, this results in huge communication blow-up, which is O of ny. So we have to find somewhere to strike a balance between computation cost and communication cost. So they introduce another factor, which is L. So client prepares this ciphertext, which is Cij, which is the power of C as well, C to the I times to the L times J, which looks very complex, but I'm going to introduce with table to make it easier. The client prepares this power of C in this way, and I is in this range, J is in this range to cover all kinds of powers. So, for example, if L is 1, clients just takes these powers in these orange slots and then sends it to the server. So then if L is small, the number of ciphertext that client sends is also small. However, the multiplicative depth is a bit large. And if L is 2, then the powers of C in these green slots are given to the server. So this is how the client prepares for the windowing technique. So with the windowing technique, communication increases with this factor, which is the range of I, which is the range of J, to the L minus 1 times log 2 ny over L. So this is really highly depending on L, and L is chosen very small in reality. So it's increased actually with this factor from nx to nx times this factor. However, the maximum number of multiplication is actually reduced. It was from log ny plus 1, and now it's log ny over L plus 1. So it is much improved. Therefore, the multiplication depth is reduced. The maximum number of multiplication was ny plus 1 in the beginning without windowing, and it's reduced to so much improved to log of ny over L. That's why the multiplication depth is also log n, which is from log to log of ny, which is so much improvement. So if we use the existing technique together, we can see how much complexity is improved. So the communication is, we have this factor from windowing technique. M over N is the factor from batching and hashing technique. And M is larger than NX, but it's not that much. So we can bound as NX as a complexity. And B is actually a factor of NY. So in total, the communication complexity is linear in the small set size and logarithmic in the larger set size because of the B factor. So the naive way was achieving the optimal communication complexity, which is O of NX. But with this optimization, the communication is a bit increased, but the computation complexity is now linear in NY compared to the naive approach, which is NX and Y, which is so much improvement. So you cannot achieve the both at the same time because anyway, it's complicated to achieve the optimal complexity at the same time. Anyway, you have the security issue. So it's better to strike a balance between communication and computation by choosing a proper parameter in practice. So this is the FHE-based PSI protocol, and this is the basic protocol actually, and afterwards there were so many improvements, but I'm just introduce the basic ones. So if you guys want to know more, if you already have this knowledge already, then you can easily follow up these other recent papers. So any question about PSI so far?
Okay, if you have any question, please raise your hand or use the chat box.
Oh, I can see the chat now. Oh, Siva, is this PSI protocol? Oh, well, with FHE, you cannot achieve malicious security directly. You need something else. So, as I said in the beginning, we are assuming that all the computing parties are semi-honest. But you can find any other papers to achieve malicious security with other cryptographic primitives.
Okay. Mahdi also has a question. It seems that the cardinality of the parties will be.
Well, in just normal PSI, yes, the cardinality is not something you hide, but there is another primitive called PSI private set intersection. Yeah, I don't remember exactly, but in this primitive, you can obtain the cardinality in a secure way. There is another primitive about it.
Okay.
Okay, can I move on?
Yeah, we can continue.
Okay, so the last section is about application to privacy preserving machine learning. So machine learning is now a hot issue everywhere, especially machine learning as a cloud service is something we want to focus on because it's a kind of outsourced computation. So with this service, we can actually predict stock price and we can filter on unwanted emails automatically. And recommender system gives us some good recommendation when we watch Netflix, Amazon Prime. They give you some recommendation based on our taste, based on what we have watched. Those are always what you can see around you everywhere, every day. However, the privacy issue is something we cannot ignore. So can we design a privacy-preserving machine learning algorithm which satisfies optimal communication and computation complexity and less communication cost, less computation cost, and also practical implementation research? This is what we want in practice. So there are many attempts already by improving the efficiency of their building blocks. So privacy-preserving convolutional neural network has been studied for so long time by evaluating sigmoid functions homomorphically and also max function as well, and finding optimal way of matrix encoding. So if you encode your matrix in a clever way, in a homomorphic encryption ciphertext, you can make use of, you can take the advantage of SIMD operation easily. So this is also a very interesting topic to be applied to neural network. And privacy-preserving KNN algorithm also exists by evaluating Euclidean distance between two vectors homomorphically. So this paper introduced a clever way to compute Euclidean distance efficiently. And also private decision tree evaluation, which evaluates comparison function homomorphically, and also the recent work which I'm going to talk about today, applies a transciphering technique to reduce communication cost. So these days, there are so many researches about achieving aforementioned properties for privacy-preserving machine learning models. So are they practical enough? In my opinion, now it's very practical enough. However, their communication overhead is still high because of ciphertext size. As I said before, ciphertext size is relatively huge compared to the underlying plain text. So because of this ciphertext size, the communication overhead is considered as impractical. It may influence on your network cost for uploading and downloading the information. But the inference phase evaluation is done in few seconds in many literatures, especially the paper that I cited here. It shows that the evaluation is done in few seconds. It sounds very practical. And also there are some optimization techniques that I've already shown in this lecture, including SIMD operation. And also these days people are trying to use this homomorphic encryption in hardware. In hardware, you can have actually at least 1,000 times faster improvement. That's why people are trying to do it. And with this hardware acceleration, you can have practical efficiency. And even though there are building blocks that I mentioned in the previous slide, even though these building blocks are optimized, there are still some ways to be more optimized depending on some application scenarios. So I'm going to talk about it now. So we're focusing on machine learning as a service because it's an outsourced computation. So in this scenario, server holds a machine learning model and a client wants to evaluate the prediction and inference using server's model without revealing its data to the server. So we have to focus on this fact that server knows the model. Then, do we really need ciphertext operation? Because one operand is already clear text. So we don't need to stick to the expensive operation at all. So we study the most recent technique, which takes all the advantage of a server which knows machine learning model in clear text. So this is the recent paper called The Sorting Hat, which introduced computationally efficient private decision tree evaluation via homomorphic encryption. It designed an efficient homomorphic comparison algorithm where one operand is a plain text. And also it designed a fast homomorphic traversal algorithm. As a second result, they introduced bandwidth-efficient PDTE called T-sorting hat via homomorphic encryption and transciphering. So transciphering is a well-known technique to reduce the network cost of any homomorphic encryption-based protocol. But it's not, in the past, it wasn't practical enough. It was only studied in a theoretical way. But in this paper, their transciphering is practical enough, which is 400 faster than previous work. And thanks to this transciphering, their communication cost of this PDTE is 20,000 times less than previous approach. So I'm going to talk about this paper. So private decision tree evaluation is an important class of classifiers in machine learning. And as you can see the figure on the right, each decision node, there is a comparison in each decision node between a threshold value owned by a server and its assigned attributes given by a client. So one operand is given by client, and the other one is already owned by the server who computes this function. And the output of the comparison function is either 0 or 1, which denotes which child node to travel. We already saw something similar in ORAM section. And the traverser outputs a vector where the only one component corresponding to the classification label is an encryption of 1, and the rest are encryptions of 0. This is how private decision tree work. So as a building block, we need a homomorphic comparison, because in each node, you do homomorphic comparison here. So normally, homomorphic comparison takes two ciphertexts and outputs a ciphertext which encrypts either 1 or 0. If A is larger than B, it outputs an encryption of 1. Otherwise, it outputs an encryption of 0. And we have to remember that the threshold values are parts of classification model, which a server already knows. So we don't need to stick to this comparison function, which takes two ciphertexts as an input. Instead, we have to build something else, which takes one ciphertext and one plain text. And this hasn't existed before. So this is our homomorphic comparison, which takes one operand as a plain text. We are working over this ring, and here x to the n goes to -1 always. We are going to use the fact from now on. So if A is encoded as a monomial like this, A is encoded in the exponent of x. And let's say Bx is encoded as x to the 2n minus b, where A and B is same. And we do multiplication between AX and BX, then x to the A, the result is x to the A plus 2n minus b. And since A and B is same, it goes to 0. Now x to the 2n is the result, and we know that x to the n is -1. So -1, the result is -1 squared, which is 1. So we are going to play with the exponent of x by using the fact x to the n goes to -1. So likewise, we can encode B as a polynomial like the following. So we encode B in this exponent here, we put this coefficient 1 until here, from x to the 2n minus b to x to the 2n minus n. So b looks like this. So coefficient 1 is encoded until here, and the rest is 0. This is bx. And what we want is to have constant term as the comparison output of A and B, which means if A is larger than B, the constant term of AX times BX should be 1. Otherwise, it should be 0. So we're going to rearrange all the coefficient by setting B like this. So if A is smaller than B, this term which has a coefficient 1 goes to the right side, is shifted to the right side. So this 0 value goes to the constant term. And otherwise, if A is larger than B, this Bx is shifted to the left side. You can see that here. Let's say A is B plus 1. Is larger than B. So x to the A times this polynomial. So x to the A is B plus 1. So this term goes to the constant term. And we don't need to care of the rest part. So since A is B plus 1 and B is encoded like this, so the x to the A and this term goes to the constant term. So we get what we want in the constant term by doing this. So actually, the computation of this comparison function is the multiplication between two ciphertexts. Encryption of AX, not two ciphertexts, one ciphertext and one polynomial. Encryption of AX times BX equals encryption of AX times BX. Because of this fact, we're just running this multiplication between one ciphertext, one polynomial. It outputs what we want on the coefficient term. So this computation only needs 2 polynomial multiplications because the ciphertext that we use is a vector of dimension 2, and each element is a polynomial. So this has 2 polynomials, and we do multiplication component-wisely. So this comparison needs 2 polynomial multiplication. And the existing works has so much complicated circuits and which has large multiplication depth. But with using the fact that B is known to the computing party, then we only need 2 polynomial multiplications, which has so much improvement. If A is not encoded as in the exponent, instead, if A is binary decomposed like this and encrypted as bit by bit, like encryption of epsilon0 to encryption of epsilon log A, then we have to tweak the bitwise comparison method. So bitwise comparison method starts from the most significant bit and gradually proceeding towards lower significant bits until an inequality is found. Let's see the example here. So let's say A and B is represented like this, and those are bit representation of A, B. And xi is defined as an XNOR value of AI and BI, which means if AI and BI is same, it outputs 1. It's a negation of XOR. Otherwise, it outputs 0. And the bar of BI is negation of BI. So those are the requirements to compute A and B bitwisely in a clear text mode. I'm not talking about homomorphic comparison yet. I'm talking about the clear text mode first, and then we are going to tweak this in homomorphic way. So to compare A and B bitwisely, you need such ingredients. And let's say A is larger than B, and A3 is 1 and B3 is 0. So we have already inequalities found. So which means X3 is 0 because they are two different bits. So all the terms which have X3 is gone. And since A3 is 1 and B3 is 0, the negation of B3 is also 1, so it outputs 1. So this is how the bitwise comparison works. So you don't need to remember everything here. I just wrote it because I need to show what is reused in our scenario. So we have to tweak this, what I said, to the homomorphic way. So homomorphic XNOR is actually easy. So B1, in our scenario, B part is known. It's not encrypted at all. And A is encrypted. So the computing party knows one operand in the clear text. If BI is 1, it only outputs the other input just without tweaking anything. It makes sense because if AI is 1, then since they are same, it should output 1, which is encryption of AI. If AI is 0, they are different. So the XNOR value should output an encryption of 0, which is encryption of AI. So this is very simple. Depending on BI, it just outputs an encryption of AI. And if BI is 0, it just negates the encryption of AI, which is encryption of 1 minus AI. So actually building homomorphic XNOR gate is very simple. It doesn't require any homomorphic operation here. So let's think about this scenario. We have 3 values here, A, B, and C. And we want to compute the comparison between A and B first. Then we want to compute A and C. And B and C are clear text. We are using encryption of A twice. And B and C has common most significant values. 1, 0, 1, 0. The 2 first most significant bits of B and C are same. We can think about this scenario. So after computing this first, we already know X3, X2, which is the XNOR value of A and B, the most significant bit of A and B, and the second most significant bit of A and B. And A3B times negation of B3, and A2 times negation of B2. Because we already computed this when we compute this first operation. So we already know this value. And to compute this value, we can reuse everything, these 4 values, because B and C have the same most significant bits here. That's why we can reuse the computed value in advance. And this is possible because B and C are clear text in server's view. So this is how we can get improvement. And another building block is homomorphic traverser. This is actually the same as homomorphic demultiplexer that I explained in ORAM section. So the goal of this algorithm is to copy the value of the root to the desired leaf of position. And each decision node contains a pre-computed function value, which is a bit, well, encryption of bit, called controller bit, and an empty slot. And the root value, which is denoted by B, is copied to the empty slot of the right child node if the root controller bit is an encryption of 1. Otherwise, it goes to the left child node, and the right child node's empty slot remains empty. So we start at the root and repeat the process until the leaf nodes are reached. And the only one leaf is an encryption of B, and the rest are encryptions of 0. So this is what I explained already in ORAM section. So depending on the controller bit, the value of root goes to the right child or left child node. Since it is an encryption of 1, the B value goes to the right child node, and the left child node remains 0. And since here the controller bit is 0, the value here goes to the left child node. This is here in this paper is called homomorphic traverser. So this is how sorting hat works. So clients encrypts its attribute vector X, and then it sends to the client server. The server initializes all the node values to 0 except the root. And the server computes homomorphic comparison in each decision node by taking corresponding attribute element and threshold value. This threshold value is public for server, and this attribute vector is encrypted. So we can use our optimized version of a homomorphic comparison function to output this CI. The CI will be the controller bit for the homomorphic traverser. So each decision node has corresponding controller bit, which is an output of homomorphic comparison. So this homomorphic traverser takes all these controller bits and the root value 1. So finally, the 1 is copied to the desired leaf, which can be the output of this homomorphic traverser. And the rest are 0. And the server computes dot product between these leaf elements and tau vector, where tau is a vector consisting of the corresponding classification label. So since here is 1, and after the dot product, the classification label correspond to this position is sent to the client. Now, to reduce the network cost, we use the well-known technique called transciphering. It's because FHE ciphertexts are really big. We have to reduce somehow to get some upload speed and downloading speed. Transciphering is actually changing the ciphertext format from symmetric key ciphertext to FHE ciphertext homomorphically by running the decryption of the homomorphic scheme. So to do this, client encrypts its data with symmetric key ciphertext. So since you guys already know that symmetric key ciphertext doesn't have a ciphertext expansion, the size is the same as plain text. So we can get optimal size of optimal complexity of communication. However, as client also has to prepare another key element, which is an encryption of symmetric key, the encryption key of this symmetric key crypto system. So this the encryption key of this symmetric key crypto system should be encrypted under FHE. Then, with this or the ingredient, server runs homomorphic decryption of this symmetric key crypto system with the given key and the ciphertext. Then automatically it outputs a FHE ciphertext encrypting the same message. This is how transciphering works. However, previously the transciphering instantiation didn't have much practical numbers. That's why it's considered as very impractical. Theoretically, it's ideal, but it's not ready to be deployed or applied to the real-world crypto system because of computational overhead. However, we consider Phillips cipher, which is a stream cipher specifically designed to be evaluated with the underlying FHE scheme. So this is actually designed for transciphering, so it has some properties of for FHE friendly design. So this is called FHE friendly symmetric key cipher. So Phillips cipher looks like that. So it looks very complex, but indeed, this function f, computing function f, is quite annoying. The other parts can be done very easily. It actually doesn't require any homomorphic operation. It's just instantiated with just while and if loop. It doesn't require any homomorphic operation. However, the computing f function is actually defined as like this. This f is called XOR threshold. It takes a public KDS information and input Z, and it takes first K elements to XOR, and the last S elements, we run this T function. T function is defined as like this. It takes input a bit string, and then it first computes the Hamming weight of this string, and then it compares if this Hamming weight is larger than the public D, which is public to server, to the computing party. So this is just homomorphic comparison. Once we have encryption of Hamming weight, we can run homomorphic comparison function easily that we defined before, because this is ciphertext, but the other operand is clear text. It's a public information. But in the past, the other previous works which designed this Phillips cipher and tried to do transciphering, they designed this XOR with so large multiplication depth. Indeed, actually, it's an addition. It can be instantiated with addition of homomorphic addition. And also, their design of T function has large multiplication depth as well. That's why the previous result was not considered as practical solution. However, we can instantiate this XOR with just homomorphic addition, and this threshold value is done by running homomorphic comparison function, which I defined before. So that's why we get so much improvement. The timing, the previous work, it took 1 second. However, with our so much powerful homomorphic comparison function, we have only 2 milliseconds. So around 400 times is improved. So this is the implementation result of sorting hat. So we use the same data set as previous works used. And D is the depth of tree, M is the number of decision nodes, N is the number of attributes. And the input of client is encoded in the exponent of X, as we did, so that we can use the fastest comparison algorithm for our implementation. So the previous works used 16 cores to implement their result. However, with only 1 core, we have already so much fast implementation result. 42 milliseconds for depth of tree, and the previous work has 940 milliseconds, and even more when the depth is large. However, also we can use parallel computation, so it can be improved more. Yeah. So compared to the previous result, thanks to our fast comparison and efficient homomorphic traverser, we can gain so much computational result, small numbers as our computational result. And when we apply our transciphering to our sorting head, we have to tweak something. Well, thanks to the transciphering, the communication cost is reduced about to 20,000 times lower. However, the transciphering outputs an encryption of bit representation of A, not A itself. Before, in just normal sorting head, we didn't use transciphering. That's why client just can encode this attribute in the exponent of X. However, after transciphering, it outputs only bit information of the attribute. That's why I explained the bitwise comparison in our scenario. So in this case, we have to use plain text ciphertext version of bitwise comparison. So since this bitwise comparison is not that optimized well, we cannot gain much improvement in here, but it outperforms the naive approach, which doesn't use the reusing technique. Since as I said before, if we are reusing the same attribute vector and the two different operand, B and C, and where B and C have some common bits, then we can reuse something computed in advance for the next step. So this is denoted by the recursive way. So if we use this technique, normally it doesn't have much improvement. But here, in artificial data, we gain this approach outperforms the naive approach. This is the case when the number of attributes are actually smaller. The number of attributes is way smaller than the number of decision nodes, which means with high probability, some attributes are reused in the decision node, in many decision nodes. So in this case, our recursive way outperforms the naive way. But still, it looks like the number is larger than the previous work. However, they use 16 cores. In our case, we get this number with 1 core. So if we use multiple cores, then of course our number will outperform. So this is the last section. Is there anything?
Thank you very much. Yes, we have 2 questions. Do you want me to read, or you maybe?
Yeah, I can read now. Can we use some more comparison between 2 ciphertexts? No, this is only designed for a comparison between one ciphertext, one plain text.
And by doing a subtraction of 2 ciphertexts and comparing the results by 0 with I think it follows from the previous question.
But I have to, I'm sorry, by doing...
Sufyan, do you want me to activate your microphone? If you want, you can unmute your microphone. Now you have access if you want to talk.
Yes. In fact, I was wondering if we can do an homomorphic comparison between two ciphertexts by doing a subtraction of the two ciphertexts to compare them by 0.
Mm-hmm. Now I understand what you mean by using the same technique. Man.
Yeah,
it's true. Yeah, you can use it as well in two ciphertext settings.
Okay, thank you.
There is another question from Kilian. What about data pre-processing in machine learning approaches via homomorphic encryption?
Data pre-processing.
Kilian, I'll also activate your microphone. If you want, you can talk. Please unmute your microphone and talk if you want.
Do you hear me?
Yeah.
So my question was just to know how we can make data pre-processing. So, for example, section features if the data are encrypted. So, is there any way for that?
I don't really understand what data processing means.
So before to train a machine learning algorithm, so selection the best features for your model.
You mean training part?
Yes, but just to select the best features to delete some outlier data. And,
well, for the training, there are some research which did training via homomorphic encryption, but yeah, I don't really follow the research, so yeah, I don't know in detail.
Okay, thank you.
Okay, thank you very much for your excellent talk. Let's thank the speaker. We enjoyed it. Thank you very much. Do you have anything to say? Or I don't know if you want to say goodbye or conclude the presentation.
Thank you for inviting me and listening to this talk for 2 hours. Well, actually, you guys were here from morning, right?
Thank you very much. Yeah, I know that it's very hard to talk 2 hours virtually because you don't see the audiences. But thank you anyway. So it was the last session of the Winter School, and as closing remarks, maybe I can say just something, and I just want to acknowledge people. So we thank all people who contribute to the Winter School, especially our great speakers. And I also thank the organizing committee on behalf of the Iranian Society of Cryptography, especially Karim Baghdari, our colleague at COSIC Leuven. He put a lot of attempts in preparing this winter school. And also we had a pre-school event for students who live in Tehran. It was a great event, and we thank all of the speakers. And also we had several students at Sheikh Bishri University who helped us for preparing this winter school. Frequently, we have been asked that about slides and videos. Videos will be available next week, hopefully, in YouTube and Apparat for Iranian. With the ID of ISC is Encrypt, and also we will add the link to the website and its slides. Those slides that we had, they are now available in the website of the school, and the others hopefully will be available as soon as we get them. Finally, we will send an evaluation survey to you. Please, it's an online form, and please participate. Evaluation and give us feedback. It lets us to prepare ourselves for the next winter school. We hope to see you again in the next winter school in 2024. Yeah, and that's it. Karim, do you have anything to add as a conclusion?
No, just yeah, I just wanted to also thank you, Hadi, and all the participants. And unfortunately, we couldn't have you in person. I mean, hopefully next time we will try to have at least hybrid. And
Yes.
unfortunately, we couldn't tag the speakers, but maybe we should mention that we will try to at least send a small gift to the speakers to thank them. I mean, they did a great job.
Yes. Okay. Thank you, everybody, and goodbye, and hope to see you in person next